The purpose of an energy audit is to help the operator to reduce the electricity consumption of pumps. It evaluates the specific energy and efficiency of each pump. This then allows us to identify pumps whose efficiency has decreased with time and to calculate additional costs that may be caused by this. The operator can then identify which pumps need to undergo maintenance or be replaced. This leads to significant savings to be made in a water utility's operating costs. Now, in this video, we'll be looking at what data is needed for an energy audit and how to use this data to calculate additional costs incurred and to plan maintenance and replacement operations. Additional operating costs are caused by the reduced efficiency of equipment used by a water utility at a given site. In the water sector, additional costs are mainly generated by electric pump units whose efficiency and specific energy are far from being optimum. In order to determine the additional energy costs, the theoretical efficiency of pumps should be compared with their real efficiency. Now, this is done by measuring various parameters. These include the discharge flow rate, the discharge volume, the suction and discharge pressures, as well as the pump's total dynamic head, or TDH, the pump's daily, monthly, and annual cumulative operating time, and the electricity consumed by the pumps, as well as several electrical parameters such as voltage and current, the price per kilowatt hour and of reactive energy as billed by electricity suppliers of the site. Thanks to these parameters, the true efficiency can be determined as well as each pump's specific energy. The specific energy is obtained by dividing the electric pump unit's power by the discharge flow rate and TDH. The power is expressed in watts. The flow rate is expressed in cubic meters per hour. The TDH is expressed in meters of water column. A pump's specific energy is thus expressed in watt-hour per cubic meter of water column. The electric pump unit's true global efficiency is then obtained by the following relationship. The true global efficiency, written as eta, is equal to 2.725 divided by the specific energy. A specific energy of 2.725 watt-hours per cubic meter per meter of water column corresponds to an efficiency of 100%. Now keep in mind that the electric pump unit's global efficiency is also equal to the motor's specific efficiency multiplied by the pump's specific efficiency. The specific energy values and the true efficiency may then be compared with reference values for similar new and in-service equipment. The reference values allow us to evaluate if the pump's actual performance is good, average, or poor for a set discharge flow rate or operating range. When the true specific energy value is average or poor, the difference with the good efficiency value enables the extra energy cost generated by the pump's deteriorated performance to be evaluated. Using the difference observed, additional costs are calculated by multiplying the TDH and the discharge rate in order to obtain the power in watts. Now, this power is then multiplied by the average operating time of the electric pump unit in order to determine the electricity consumed in watt-hours. By knowing the price of a kilowatt-hour, it is possible to calculate the additional cost that this difference in specific energy represents, and thus the effect of a pump's reduced efficiency on operating costs. Once all the electric pump units have been evaluated during an energy audit, they can be ranked according to their efficiency, but more importantly, by the additional costs that they generate. Now, this ranking helps in properly planning maintenance and renewal operations, as well as investments which must be done to improve the energy efficiency of specific sites. Here's what you need to remember. An energy efficiency audit allows a pump's true efficiency to be determined thanks to hydraulic and electricity measurements. This true performance linked to two indicators, i.e. global efficiency and specific energy, may then be compared to target values used to rank pumps into good, average, or poor performance categories. Additional energy costs may then be calculated for each pump ranked as good, average, or poor, which then enables priority power pump units to be identified, for which the operator can make significant savings in terms of energy-related operating costs.